grade 11s, welcome to another video. I am Miss B and this is Miss B's Hive. Hopefully you become one of our buzzy bees by subscribing to my channel, liking this video and turning on your post notifications so you get a notification every time I post a new video. Alright, so today's lesson will discuss polar and non-polar molecules. So I would like to bring your attention to these particular words, right? So polar in the case of chemistry looks at poles of positive or negative. Now in previous lessons I have went through electronegativity. You can go back and watch that video, and I have discussed electronegativity and the different atoms on the periodic table, or other elements that are highly electronegative. Now, to define it, polar molecules have an unequal sharing of electrons and non-polar molecules, they have an equal sharing of the bonding electrons. Okay, so the electrons unequal sharing of, I would also like to replace this with unequal sharing of bonding electrons. Alright, so that's the main difference. Now, in a polar molecule, there is something that is called a dipole that forms, and in a non-polar molecule, we have no dipole forming. So essentially, what polar means is that one of the atoms will have a stronger or weaker pull on the electrons that are bonding or that they are sharing in a covalent bond. And then non-polar says that they are equally pulling on the electrons. So no one atom has a stronger pull than the other. Right, so let's just erase the board and go back to explaining this difference. Okay, so for polar, we say that one atom is more electronegative, and that causes a dipole, right? And then on my non-polar side, they are equally sharing. So if I were to think of examples where there would be equal sharing, those would be my diatomic molecules, right? Because that would have an equal number of electrons surrounding that particular molecule, right? Even if I were to look at HH, that means these bonding pairs here are shared equally. Whereas on the polar side, I would look at something like HF. Now, hydrogen, we know, has only one electron that is in this bonding pair, but this fluorine still has a good 3 lone pairs around it. Alright, so what this would mean is that this part of the HF molecule, because fluorine is more electronegative, it will pull the electrons close to it, right? And then that would simply leave this side what we call slightly negative, and this side where the hydrogen is would be slightly positive. So those are what we call dipole. Now in the name, in chemistry, di means two and pole means positive and negative. So the molecule has two poles which are oppositely charged, one being positive and one being negative. So you have to look at which one is more electronegative and which one will pull this bonding pair more closely and form a slightly negative dipole, and then on the H side it will form a slightly positive pole because the bonding electrons have moved a bit away from the hydrogen atom. Alright, so I hope that makes sense. I'm going to write down some more examples of all the key differences or examples of polar and nonpolar for you. So I've said the diatomics are nonpolar, as well as there are other types of molecules, right, which goes back to something called the VSEPR theory. So we know all the diatomics or diatomic molecules, they will share electrons equally. But I also have examples like BF3 and CCl4. So let's draw this out. So for BF3, it will look like this. The boron, so this, remember, is a Cooper model. We usually draw with Lewis. So in the Lewis dot, that would be boron is in group 13. So it will have 3 valence electrons. And it will have 1 fluorine there, 1 here, and another there. So for the fluorines, I'll just draw them in with this blue, right? And then I will use this to explain how non-polar molecules form. Now, this, I've drawn it for you in a Cooper model. It's easier to see the molecular shape like this. So this shape is known as trigonal planar, and it's in the name, right? Tri meaning 3, 3 atoms around a central atom. So the boron here is the central atom, and the fluorines would be the terminal atoms. So this shape that has boron with the 3, so something like that, that is called trigonal planar. Now for trigonal planar, I want you to draw your attention to the central atom boron. If you look closely, boron in this particular compound does not have any lone pairs. So it has only 3 valence electrons, which are the black dots indicated there. And those black dots, there are no other electrons around boron. They are all bonding. So this BF3 forms an ideal shape, and the name of the ideal shape is trigonal planar. Now, ideal shapes and the names come from the VSEPR theory. So I'll try to insert it for you so you can see where it's coming from. But these ones have anything that is on the VSEPR theory has no lone pairs on the central atom. Now if you look, there are lone pairs, but they are around the fluorine atoms and not the central atom, which in this case is the boron. So whenever you're looking at a molecule and you're drawing its Lewis dot and there are no lone pairs on that middle one or the central atom, that means that it forms an ideal shape according to the VSEPR theory, and in our case here, it is trigonal planar. Now, molecules that form ideal shapes are said to be symmetrical. So in explaining nonpolar molecules, you always need to look at what shape does it form. If it does form an ideal shape, you need to name that shape and then explain that the shape is symmetrical as there are no lone pairs on central atom. And if I were to cut this atom, it would be perfectly symmetrical. So that's what it means by symmetrical. If I were to divide it up, each part would be sharing the electrons equally. So that is considered a non-polar molecule. Now you can go and find the bond polarity between the boron and the fluorine using the change in En and find out bond polarity. But in this video, we are discussing molecular polarity, and I hope that you are able to see that those are completely different things. All right, so let's go back and do another example of non-polar molecules and explain its molecular polarity in words. So I'm going to draw for you the other example, which is CCl4. So carbon is my central atom and it has 4 valence electrons. Around this carbon are chlorines, right around, and my chlorines have 7 valence electrons around them. I'm just going a bit faster so that I can make this a shorter video. Right. Now, if I look at this molecule, let me draw the Cooper model so that you can see, which, remember, these lines mean a bonding pair, these pairs. So this line represents those bonding pairs over there. So it looks something like this. Right. Now, in a Cooper model, we only show the bonding electrons or the bonding pairs, and we show them with these black lines. Now, remember what bonding pairs are? Those are the pair of electrons that participate in a chemical bond or that are shared between different atoms. Now, this has a perfectly symmetrical shape. Now, anything that is AX4 as the general formula, meaning a subscript of 4, right? And you need to do this and master it because you can't just guess by looking at the subscript that it would be polar or non-polar. You actually have to draw the Lewis dot so that you make a correct conclusion about whether you're explaining if it is polar or non-polar. Right, so this shape from the VSEPR theory, if you look at the central atom here, the carbon, it has no lone pairs. All 4 of the carbon's valence electrons here in the red are bonding to the chlorines. So there is no pair that is unbonded. So that means that it has no lone pairs. So that's something that you can note when you're explaining. I'm writing in shorthand. You would need to explain it in paragraph form, which I'll do at the end. No lone pairs. Then you need to say that the shape that it forms according to the VSEPR theory is tetrahedral. Now, tetra in chemistry or in physics means 4. So tetra means 4, and you can see that there are 4 chlorines around the central carbon. So it has no lone pairs. According to the VSEPR, it is tetrahedral, so that makes it symmetrical. so that's a symmetrical molecule. And that means it has no net dipole, making this overall molecule non-polar. All right, so if you were to explain this for your exam, you would start off by saying that CCl4 contains no lone pairs around the central carbon atom. Therefore, we can see that it forms an ideal shape according to the VSEPR theory known as tetrahedral. This molecule is symmetrical, meaning that there is no net dipole moment, and therefore this molecule is non-polar. So do you see, if you explain it like that, you will get all the marks because you've covered everything that is relevant for it. So I've only done but mere 2 examples, and I can do the one for the diatomic molecules very quickly here in blue. Let me just erase this polar so that you guys don't get confused. Let's look at BR2. Right. So if anything is next to each other like that, or its Lewis dots representation would look something like this, right? Then it is in a line, which makes it linear according to the VSEPR. And linear is an ideal shape. So you can also go on to say that the bromine molecule, first of all, we're going to say that it has it has one bonding pair, and it's made up of the same 2 atoms. So that means if I were to cut it here, I would get bromines that look exactly the same, which makes it symmetrical, right? And for it being symmetrical, it means there's no dipole moment, which means the dipole moment will be 0. And because it is symmetrical and it is a linear shape and there's no dipole moment, we can conclude that this is a non-polar molecule. Right, so that's how you do non-polar molecules. These are just but a few. I really do hope that it's clear now, especially how to write them. I've used point form, you can see over here. But when you explain it in your exam, you'll have to go back where I was actually reading out the answer to you and write it down so that you can practice. Alright, so next up I'm going to do polar molecules with you and explain how to determine the molecular polarity of polar molecules. So first up, we are now looking at polar. We've just looked at non-polar. And remember, I said there's a slightly positive and a slightly negative dipole that forms. All right. So the examples that I have for you here are HF. Now let's see. HF is hydrogen and fluorine, right? I've done this one in the previous one, but I just want to recap quickly. The shape here is linear. However, this one is more electronegative. So in your explanation, you will say that HF is linear. You make reference to the shape. Then you say that the fluorine, the F, is more electronegative. Meaning, so you have to explain, meaning it pulls bonding pair closer, creating a dipole moment. Right, so if I were to draw how exactly my HF would look, I just want to get that nicely. I would have slightly positive, and then I have to draw this arrow with the line here, which indicates that a dipole moment has formed. All right, so essentially what I was trying to draw. All right, so if I look at what I've done here, is I'll just explain quickly. I've inserted two pictures, right? One of water and one of this HF molecule, which I was showing you guys. So I have to show an arrow when I'm drawing that indicates that moves to the more electronegative one. So that simply means that because the fluorine has all these electrons around it, it has a high electron density, which means it'll have a stronger pull on the shared pair, which is this, and therefore it'll form a slightly negative side charge, and on the side where the hydrogen is, it'll form a slightly positive charge. Now let's look at the water. I'm going to draw in those lines or those arrows that point to show that a dipole is forming. And if you do know your work, you will know that there are two pairs of lone, remember, there are lone pairs on the oxygen atom, meaning that the oxygen atom has electron density, which means it has much more electrons than the hydrogen, making it slightly negative, and the hydrogens will now be slightly positive. Alright, so I have a few more examples. Let's do them together. Two more, the famous ammonia as well as another one. So this time I'm going to show you how to explain the molecular polarity as well as draw them. Okay, so let's just do this. On this side I'm going to have CH3Cl, and here I'm going to draw my NH3. Alright, so let's start off with the ammonia. I'm going to draw in the ammonia. Now you will see that ammonia, I made a mistake there, sorry about that. The ammonia has 5 valence electrons around it, and then it is paired with 3 hydrogens around, and it has this lone pair at the top. Now if I were to draw a diagram to show, let's do a Cooper model, you will see that it looks something like this. Now this is what we call a non-ideal shape, right? So it is non-ideal. It actually has this bent shape. Now where does the bending or bent come from? This lone pair of electrons here makes this molecule automatically to be polar. Now, so what are the things to discuss with the discussion points? You'll start off by saying that ammonia has 1 lone pair of electrons. Please don't write pair. Remember, are you talking about shoes or are you talking about electrons? So it has 1 lone pair of electrons. Also, it is a non-ideal shape due to lone pairs. So it therefore forms a dipole where the nitrogen is slightly negative and the hydrogen is slightly positive, meaning there's a net dipole moment. Therefore, it is a polar molecule. Alright, so essentially that's how you would go about explaining this particular molecule. Now the lone pairs there will be slightly negative, and then these will be all slightly positive because all the electrons have moved or pointed away towards the nitrogen. Okay, so let's go to the side. I'm going to draw in. Carbon has 4 valence electrons. Then it says that there is 3 hydrogens and a chlorine. Right, so let's see. Let's draw it this side with the dipole moment. So you can see. Now obviously that would be slightly positive, slightly positive, slightly positive. But here, slightly negative. Because what would happen is that the chlorine will have a stronger pull on the shade pair because the chlorine is more electronegative. So I'll start off by saying, if I look at the shape, it does form a tetrahedral. So ideally, because it forms an ideal shape, it is supposed to give me a non-polar molecule. But I hope you can see, grade 11s, that this is completely different to when I had the previous examples. I have three different atoms with different electronegativities that are bonding. So naturally, the chlorine is more electronegative. I'll just start off by saying that. Then, because to show your examiner that you understand your work, you will say that it has a tetrahedral shape. But, and this is a very big but molecule is not ideal due to the net dipole forming, where you can see that the chlorine is slightly negative and the hydrogen is slightly positive. So therefore it can be concluded that this is a polar molecule. So this is a very good example because although it is a ideal tetrahedral shape, it's not non-polar, but in fact polar due to this highly electronegative chlorine. So I do hope you understand that. Okay, so now I'm going to summarize everything that I've said so far. Okay, so first up, something can have polar bonds. And how will you find the bonds? You will find the change in electronegativity. That's the bond polarity, right? And you can go and watch my previous video on bond polarity in electronegativities. So something can have polar bonds, but due to shape, it can be non-polar molecule. And then I can have polar bonds, right? And a polar molecule. So not all molecules with polar bonds will be polar, and not all non-polar bonds will form non-polar molecules. So you need to remember that the polarity of the molecule is determined by the following things. So how do I explain molecular polarity in my exam? So I have to make reference. So molecular polarity has to do with the shape and if there's a dipole or not. So when you are explaining, the first thing you're going to look at is you can explain the bond polarity using the electronegativity difference. You will also have to explain this answer. So reading the question, what is, or compare the molecular polarities. You're looking at bond polarity. You have to look at shape, right? So if there are lone pairs, that is usually a bent or angular shape, like water and ammonia and SO2. Right? And if there are no lone pairs, we know that it forms a ideal shape that you will find on the VSEPR theory. So you will discuss the shape. If I have water, you will say water is a bent molecule, or water's geometrical molecular shape or molecular geometry is angular or bent, preferably right bent. After discussing the shape, you will have to see if there are lone pairs, and you'll have to look at if there are elements with a high electronegativity. Thereafter, you must determine if a dipole has formed, and depending on if a dipole has formed or not, you will discuss symmetry. Well, under shape, you have to discuss the symmetry of the molecule. Is it asymmetrical or is it symmetrical? Meaning, if it is asymmetrical, it's due to lone pairs or unequal sharing of electrons. But symmetrical means that if I were to cut that shape in half of that molecule, I would see the exact same thing on either side. And that is when there are no lone pairs. So when you have to determine whether a dipole has formed, and then lastly, you can make the conclusion whether it is polar or non-polar. And all of this is relating to shape. Molecular polarity has to do with shape. So for this, your key skills you need to know is Lewis dot. And then you need to know VSEPR theory. And you also need to know electronegativity. Alright, grade 11s. I really hope you enjoyed this video and that you do give it a big thumbs up. And I hope you subscribe to the channel, and I hope that you keep on studying. And remember the key skills: Lewis dot and VSEPR. So let me try to insert what VSEPR says briefly. Alright, so I've inserted here the ideal shapes that form from the VSEPR theory. You need to know these shapes. So we have linear, trigonal planar, which refers to 3 atoms around a central atom. Tetrahedral, tetra means 4, tri means 3. gonal bipyramidal. This is a bit of a tricky name, but if you look at the prefixes, 3 from tri plus bi means 2. 3 plus 2 is 5. And the last one is octa, but we know octa usually in English means 8. But in the case of these shapes, octa means 6 around a central shape. The bond angle you don't really need to know, but it is in your best interest to always study and be prepared as possible. But this is the VSEPR theory in summary, and these are the ideal shapes. You need to know names, you need to know the general formula, and you need to have an understanding of the fact that everything on this table has no lone pairs on central atom. Therefore, they are symmetrical and they have no dipole, and they are ideal shapes. Alright, so I hope you enjoy this video. You give it a big thumbs up. You comment down whether you're enjoying these videos that I'm posting so I can continue posting them. Please like them, share them with your friends at school. And I really do hope they help you in your preparation for studying for your physical science chemistry paper 2 examination. And yeah, please feel free to drop a comment down below. If you've watched this video up to this far, please insert a book emoji so that I know that you have watched it up to this far and that you will enjoy watching this video. Until the next one, peace.